Download this code from codegive.com, link in the description below. Achieving enhanced detail with 2x zoom, a comprehensive tutorial. This tutorial dives deep into achieving enhanced detail when zooming into an image, specifically targeting a 2x zoom factor. We'll cover various image processing techniques, focusing on sharpening and upscaling, along with practical code examples in Python using popular libraries like opencv, cv2, and scikit-image. Understanding the problem, zooming and information loss. When you digitally zoom into an image, you're essentially enlarging the pixels. A simple zoom, like nearest neighbor interpolation, just duplicates pixels, leading to a blocky, pixelated, and unnatural look. This is because you're not actually adding new information, you're merely making the existing pixels bigger and more visible. The goal of detail enhancement at 2x zoom is to approximate the information that should be present in the enlarged image, creating a more visually appealing and informative result. Techniques for enhanced detail. Several techniques can be employed, often in combination, to achieve a more detailed and visually pleasing 2x zoom. 1. Interpolation techniques * beyond simple nearest neighbor, more advanced interpolation methods like bilinear, bicubic, and Langcho's resampling attempt to estimate pixel values between the existing ones. 2. Sharpening * sharpening techniques enhance edges and fine details, making the zoomed-in image appear crisper and more detailed. 3. Super resolution (SR) methods * these are more advanced algorithms that attempt to infer higher resolution images from lower resolution inputs. They often rely on machine learning and can produce impressive results, but they're also computationally more intensive. 4. Contrast enhancement * adjusting the contrast of the image can bring out subtle details that might be obscured. 5. Noise reduction * noise can be amplified during zooming and sharpening, so pre-processing to reduce noise can be beneficial. Implementation in Python with opencv and scikit-image. Let's explore how to implement these techniques using Python with opencv, cv2, and scikit-image. 1. Setting up your environment ***. First, you'll need to install the required libraries. 2. Basic image loading and display ***. 3. Interpolation techniques ***. opencv provides various interpolation methods. *cv2.inter_nearest, nearest neighbor interpolation. Fast but produces the most pixelated results. *cv2.inter_linear, bilinear interpolation. A good balance between speed and quality. *cv2.inter_cubic, bicubic interpolation. Slower than bilinear but generally produces better results. *cv2.inter_Langcho's 4, Langcho's resampling. Usually the slowest but often the best quality for upscaling. Observe the differences between the results. You'll see that nearest neighbor is the blockiest, while Langcho's generally provides the smoothest and most visually appealing upscaling. Bilinear and bicubic offer trade-offs between speed and quality. 4. Sharpening techniques ***. Sharpening enhances edges and fine details. A common method is using a Laplacian filter. opencv offers the cv2.filter2d function for applying custom kernels. Experiment with different sharpening kernels to find one that works best for your image. Be careful not to over-sharpen, as this can amplify noise and create unwanted artifacts. 5. Unsharp masking, a more controlled sharpening technique. Unsharp masking is a more sophisticated sharpening technique that allows for more control over the sharpening process. It involves blurring the image, subtracting the blurred version from the original, creating a mask, and then adding a weighted version of the mask back to the original image. Adjust the sigma and strength parameters to fine-tune the sharpening effect. Higher sigma values blur the image more, while higher strength values increase the sharpening intensity. 6. Contrast enhancement. Adjusting the contrast can bring out subtle details. A simple technique is histogram equalization. CLADHE, contrast limited adaptive histogram equalization, is a more advanced form of histogram equalization that avoids over-amplifying noise by limiting the contrast enhancement in local regions. 7. Noise reduction. Noise can be amplified during upscaling and sharpening. Applying noise reduction beforehand can improve results. Common noise reduction techniques include Gaussian blur and median filtering. Noise reduction can be beneficial, especially for images with significant noise, but be careful not to oversmooth, as this can blur fine details. 8. Combining techniques, a complete example. This enhance_zoom_2x function combines the techniques we've discussed, allowing you to easily apply a series of enhancements to a zoomed-in image. Remember to adjust the parameters of each technique to optimize the results for your specific image. 9. Super resolution, SR, with deep learning, optional. For even better results, especially when starting with low-resolution images, you can explore super resolution techniques based on deep learning. These models are trained to predict high-resolution images from low-resolution inputs. *SRAGN, Enhanced Super Resolution Generative Adversarial Network, a popular and powerful SR model. You can find pre-trained SRAGN models and implementations online. Libraries like RaySRAGN provide easy access to SRAGN functionality. Installation, pip install RaySRAGN. Here's a basic example using RaySRAGN. You'll need to download the model first, see the RaySRAGN documentation. Important considerations ****. Image type ***. The best techniques depend on the type of image. Photographs may benefit from different settings than images of text or graphics. Computational cost ***. More advanced techniques like SR require more processing power. Consider the trade-off between quality and speed. Experimentation ***. The optimal parameters for each technique will vary depending on the image. Experimentation is key to finding the best settings. Artifacts ***. Be careful not to over-sharpen or over-enhance contrast, as this can introduce unwanted artifacts. GPU acceleration ***. For computationally intensive tasks like SR, using a GPU can significantly speed up processing. Summary ***. Achieving enhanced detail with 2x zoom involves a combination of interpolation, sharpening, contrast enhancement, and, optionally, noise reduction. By carefully selecting and tuning these techniques, you can significantly improve the visual quality and information content of zoomed-in images. For the highest quality results, explore super resolution methods based on deep learning, but be aware of the computational cost. Remember to experiment and adjust the parameters to optimize the results for your specific images and application. Okay, let's dive into the world of achieving 2x zoom details in images, focusing on techniques and code examples. This is a broad topic, as the ideal approach depends heavily on the original image resolution, the desired output resolution, and the application's constraints, performance, storage, etc. We'll explore several methods ranging from simple interpolation to more advanced deep learning-based approaches. Understanding the challenge. The fundamental problem is that zooming in on an image beyond its native resolution introduces artifacts. You're essentially inventing pixel data where none existed before. Naive methods like nearest neighbor interpolation make the zoom very pixelated. The goal is to minimize artifacts and, ideally, enhance details during the zoom process. 1. Simple interpolation methods. These are the most basic methods, computationally inexpensive, and widely available. They are a good starting point, but don't expect miracles in detail enhancement. Asterisk nearest neighbor asterisk simply duplicates the nearest pixel value. Produces blocky results but is extremely fast. Asterisk bilinear interpolation asterisk averages the values of the 4 nearest pixels. Smoother than nearest neighbor, but still blurry. Asterisk bicubic interpolation asterisk a more sophisticated interpolation that considers a 4x4 grid of pixels around the target location. Provides better results than bilinear, with improved sharpness and reduced artifacts, but is slower. Code example, Python with opencv. Explanation asterisk. 1. Import libraries asterisk cv2, opencv, for image processing and numpy for array manipulation. 2. Zoom _with interpolation function asterisk. Asterisk takes the image path, zoom factor, and interpolation method as input. Asterisk reads the image using cv2.imread. Asterisk calculates the new width and height based on the scale factor. Asterisk uses cv2.resize to perform the zooming with the specified interpolation. Asterisk returns the zoomed image. 3. Example usage asterisk. Asterisk specifies the image path. Remember to change this. Asterisk calls zoom _with interpolation to zoom the image. Asterisk displays both the original and zoomed images using cv2.imshow. Asterisk waits for a key press with cv2.wait key, 0, and closes the windows. Important asterisk. Asterisk replace your _image.jpg with the correct path to your image file. Asterisk you can change interpolation method to cv2.inter_linear, bilinear, or cv2.inter_nearest to compare the results. cv2.inter_area is often a good choice for shrinking images. cv2.inter_length 4 is another high-quality option, but slower than bicubic. 2. Sharpening filters. After zooming with interpolation, you can apply a sharpening filter to enhance details slightly. This won't create new details, but can make existing edges and textures more defined. Asterisk unsharp masking asterisk the most common sharpening technique. It subtracts a blurred version of the image from the original image and adds a weighted version of the difference back to the original. Code example, opencv sharpening. Explanation asterisk. 1. Sharpen _image function asterisk. Asterisk takes the image, sharpening amount, radius of blur, and contrast threshold as input. Asterisk blurs the image using cv2.gaussian blur. The blur radius controls the range of sharpening. Asterisk subtracts the blurred image from the original, amplifying high-frequency details, edges. Asterisk adds a weighted version of the difference back to the original. The amount controls the intensity of the sharpening. Asterisk applies clipping to prevent values from going out of the 0 to 255 range. 2. Combining with zooming asterisk. Asterisk the code first zooms the image using the zoom _with interpolation function. Asterisk then, it applies the sharpen _image function to the zoomed image. Asterisk the original, zoomed, and sharpened images are displayed. Important parameters for sharpening asterisk. Asterisk amount asterisk controls the strength of the sharpening. Higher values increase the effect, but can also introduce artifacts. Asterisk radius asterisk the radius of the Gaussian blur. Larger radii sharpen larger scale features, while smaller radii sharpen fine details. Asterisk threshold asterisk controls the minimum difference between adjacent pixels that will be sharpened. This helps to avoid sharpening noise in smooth regions. A value of 0 sharpens everything. 3. Super resolution techniques, more advanced. Super resolution, SR, techniques aim to reconstruct a high-resolution image from a low-resolution image. These methods are significantly more complex than interpolation or sharpening, but can produce much better results. SR methods are generally divided into traditional SR methods these use techniques like sparse coding, example-based learning, and image priors. They often involve complex image processing algorithms. Deep learning-based SR methods these use convolutional neural networks, CNNs, trained on large datasets to learn the mapping from low-resolution to high-resolution images. They are generally the state-of-the-art in super resolution. 3.1. Deep learning-based super resolution, DLSR. This is where you'll see the most impressive results, but it also requires more effort to set up. The basic idea is to train a neural network to hallucinate the missing details when you zoom in. There are many pre-trained models available, which you can use without training your own. SRAGN, Enhanced Super Resolution Generative Adversarial Network, a popular and powerful SR model known for generating realistic textures and details. RealSRAGN an improved version of SRAGN, designed to be more robust to real-world image degradations. EDSR, Enhanced Deep Super Resolution Network, another popular architecture focusing on performance and detail recovery. Code example, using RealSRAGN with RealSRAGN and CNN Fuken. This example uses a command line utility, RealSRAGN and CNN Fuken, which is a fast, efficient implementation of RealSRAGN optimized for inference. You'll need to install it separately. 1. Install dependencies Install RealSRAGN and CNN Fuken by following the instructions in their repository, usually a pre-built executable for Windows/Linux/Mac OS. Search for RealSRAGN and CNN Fuken GitHub to find the repository. Download the correct executable for your OS and place it in the same directory as your Python script, or in a directory in your path so it can be executed from the command line. 2. Python code to use RealSRAGN via command line ***. Explanation ***. 1. Upscale _with _RealSRAGN function ***. Takes the input image path, output image path, scale factor, and model name as input. Constructs the command line command for running RealSRAGN and CNN Fuken. Uses subprocess.run to execute the command. Handles potential errors by checking the return code of the command. 2. Example usage specifies the input and output image paths. Remember to change these. Calls upscale _with _RealSRAGN to upscale the image. Displays the original and upscaled images if the process was successful. Key points about RealSRAGN and CNN Fuken installation the most important step is to install RealSRAGN and CNN Fuken correctly. Download the appropriate binary for your operating system from the releases page of the GitHub repository. Model selection you can specify different models using the n parameter, example RealSRAGN x4v3, RealSRAGN General x4v3, RealSRAGN Animevideo 3. Experiment to find the best model for your image type. Output format the output format is determined by the file extension of the output path, example .png, .jpg. PNG is generally preferred for lossless quality. Asterisk command line arguments asterisk refer to the realsregenen CNN documentation for all available command line arguments, such as tile size, GPU ID, and more. Asterisk GPU acceleration asterisk the realsregenen CNN version is designed to utilize your GPU for faster processing. Make sure you have the necessary drivers installed. Alternatives to realsregenen CNN asterisk upscale with Python libraries asterisk you can directly load the model into your Python code to avoid the command line call. This approach requires installing deep learning frameworks like PyTorch or TensorFlow and using libraries like Torch realsregen, PyTorch. Asterisk other super resolution libraries asterisk explore other super resolution libraries like scikit-image, a Python wrapper around several SR models. Choosing the right method. Asterisk low detail / low resolution source asterisk simple interpolation and sharpening may be sufficient. Asterisk high quality source with some detail asterisk bicubic interpolation and careful sharpening. Asterisk need for enhanced detail asterisk deep learning based super resolution, SRegen, realsregen, etc., is the best option. Important considerations asterisk performance asterisk simple interpolation is the fastest. Deep learning methods are much slower, especially without a powerful GPU. Memory deep learning models can consume a significant amount of memory, especially for large images. Artifacts be mindful of introducing artifacts, example ringing, over-sharpening, unrealistic textures. Training data if you're training your own super resolution model, the quality and diversity of your training data are crucial. Let me know if you have any specific requirements or constraints, and I can tailor the recommendations further. For example, if you have very low resolution images and need the best possible results, I'd focus on setting up and fine-tuning a deep learning based SR pipeline.